All right. Hi, everyone. Thanks for dropping to my talk. Today I'll be talking about how you can win with simple and even some linear models. And there's a reason why I'm a little bit passionate about this, because if you are living on the internet or in our sort of little filter bubble, you may have heard variants of this quote, something in the line of you should be using deep learning. And typically, the people who tell you this are people like blogs, Reddit, Hacker News, and some YouTube stars. And especially the latter one is kind of weird because people are rapping about variational atom encoders and stuff. And this got me thinking and actually got me inspired to talk about this because it's getting a little bit worrisome. And I love deep learning. I actually do it for clients. But to be very specific, it feels more like people are focusing about the tools that they're trying to apply than that they're trying to actually solve a nice problem. And again, I've used deep learning in production, but I prefer the simpler models. And in this talk, I hope to convince you and I hope to explain to you why. It's not like deep learning isn't amazing, like it really is, but there's a bit of hype around it that's distracting people from other great ideas. And some of those other ideas are actually greater. And you may be doing yourself a bit short if you pay too much attention to them. You can often win with much simpler models that have properties that are much nicer to have in situations beyond a Jupyter notebook. And I'm an industry kind of person. I really care about what happens in production. So my goal is to lure you back to the domain of boring, old, but ultimately beautiful, simple models. I hope we're excited about that. In particular, there's a couple of topics that I'll discuss, and I will be going over all of these things relatively quickly due to time, and I hope that I will mainly leave you with a lot of intuition. I will start by saying that XOR actually is a linear problem. I'll show you a lot of great time series tricks, especially if you're going to predict a long time ahead. I'll show you some small feature engineering tricks. We'll discuss streaming models. That's models that learn data point per data point instead of just on a large batch file. And we're also going to talk about recommenders, a video game recommender, and afterwards I'll end on something that I think might be the future of machine learning, namely hierarchical domain models. So, the XOR problem. You probably have a book on neural networks, and one of the main arguments you typically hear on why you should use a nonlinear model as opposed to a linear one is that you cannot deal with the XOR problem. And it's a textbook example, and it's something like this. So let's say that our task is that we want to predict the blue points, and we want to separate them from the red points. And then people will say, you need a nonlinear model for that, because there's no line that will separate the classes. So let's do an experiment. We put that into scikit-learn. So from scikit-learn, import linear model, logistic regression. This is a small library that allows me to say the class is dependent on the x1 and x2 thing in this data frame. I have my y, I've got my x. I check it on the logistic regression, and yes, the confusion matrix isn't great. So then what people typically do is they say, okay, let's use a model that's easier to apply than to understand. So let's maybe use a support vector machine. And then you can see that the confusion matrix is actually a lot better. What I could do, though, is if I just look at this data set, sure, right now with just these two features, I cannot separate them linearly. But how about I apply a small trick? What I'm going to do is I'm just going to say I'm going to add a third column that are based on these two columns. So I'm going to say I'm going to make a new column called x3, and it will be this number multiplied by that number. Suddenly, when I put that into this model, the confusion matrix is actually pretty damn good. So yes, XOR you can solve with a linear model. The trick here is that you just have to do a small little feature engineering trick. And that was enough to already be competing with the support vector machine. And I have a logistic regression, which is easy to explain, and less stuff goes wrong in production. I can explain it to this person in the suit that I'm supposed to convince that machine learning is great. So already I'm seeing lots of benefits by just adding one line of code. And this was this very sort of textbook example. I mean, it's just a demo of a linear method solving a nonlinear problem. But because the linear model is applied instead of a nonlinear one, we have much better interpretability, and there are many more tricks that we can use. And the main reason for me as a consultant, especially if I'm at a company who's just starting out, when I leave, I typically want my legacy to still be in production. I really like the idea that suppose the company has great engineers, but not maybe the best scientists. I can leave a linear model, and I'm pretty sure it's going to work for the next 2 years. If it breaks, they'll fix it. Complex models don't have this property. Sorry? Yeah, well, there's two types of consultants, Lev. If you're interested in this, let's discuss business after, shall we? Okay, that was the first heckle. Well done. So this is a very silly example, and what I hope to do now is to show more of a relevant example that's actually happening quite often. Who here has a situation where you want to predict a year ahead? Like if you're in retail or something like that, right, this is something you typically see. And also here, this is non-linear. I've got something here that I call x, and this is definitely not a linear relationship with x. Some things about this data set, it's fairly general, I think. Let's pretend it's daily data. We've got 4 years of it. We want to predict a year ahead, maybe 2. It's a fairly common planning task, I hope you all agree. And I also hope you can smell from here that the feature engineering will play a large role. And I'll just show you one trick that I really, really like, and then I hope we all agree that it's a nice trick and that it will mainly work in linear models. What some people do is they make a dummy variable. Hint, hint, dummy. The word dumb is in it. What they do is they say, let's take like a variable for a month in a year, and everything there will be averaged, and we kind of have a seasonal pattern. And this is true. It's not the worst idea. But I mean, the thing that I don't like about it is I do want to be able to predict from April 30th to, let's say, the day that's in the next month. And I do think that points that are close to each other should be able to influence each other, independent on whether or not there's a separating line that denotes if it's a new month. So again, we're going to do a feature engineering trick. There's a very complicated formula that's shown above. But basically what I'm doing is I've got some sort of hump that repeats itself every year. It's a radial basis function. That's another way, but just call it a hump. There's a hyperparameter called alpha that allows you to make the hump thinner or more thick. But the nice thing that I can do is I can make such a hump for every January, for every February, for every March, and all the other months. And the nice thing is, when I chuck this into a linear regression, there's something to be said. You might actually get a nice little smooth fit over the data points you're trying to predict, let's say, a year ahead. So what you would typically do is you would have some sort of function in pandas that generates these columns for you. So there's this radial basis function for January, and then all the way up to December. Let's pretend that this was the data frame that we had. And when we fit this with the normal linear regression, and that's it, this is what comes out. And definitely compared to the dummy thing that we were generating before, this looks a lot better. It's a nice smooth curve. And again, the only thing I did here was a nice little trick with regenerating features. And the cool thing is, I can actually go up to my manager and I can say, look, I filtered out the season. There might be still some pattern left, but at least I've quantified what the long-term season should be. And all of this is just a couple of lines of extra feature engineering. And, I'm willing to argue that's actually a pretty cool approach. If you tune the hyperparameter alpha that I showed before, you get these sorts of things. So you still want to do the normal feature engineering and hyperparameter tuning. But we're actually still very flexible. In fact, we're so flexible, you can still keep frequentists happy. Because when you put this in a linear regression, you can still do all the stuff you're used to doing with linear regression. So if you want to remove features that are insignificant, because we're still in the linear domain, we can actually remove some features that aren't significant, for example, which is also kind of cool. If you're into this thing. I prefer other methods, but still kind of cool that you can keep the frequentist trends along. Yeah, well, not too important. Another thing that I like about this, and it just deserves a mention real quick, all the magic can be explained, but whenever I'm at the client, I don't know for sure if they have scikit-learn, or if they've got H2O, or SparkML, or if they're just using R, or Microsoft stuff. But I'm pretty sure that whatever stuff they have linear regression. So if I'm at least able to use some of these feature engineering tricks, I'm pretty sure I'm always able to find a way to get it to production, even if they have a different stack than what I'm used to. You can implement this in Java. Or JavaScript. It's amazing. And you can mold this feature approach. I mean, right now I've generated 12 features, but you can very well imagine you might make 24, one for every 2 weeks. And you can also imagine that you have this feature for sort of the long-term thing in the year, and you've got another radial basis function for within a single day, for example. And because everything is linear, it's relatively straightforward, and I hope you agree. It's kind of a cool trick. What you can also do is you can have a separate radial basis function for different days of the week. In the Netherlands, there's this weird thing that on the Wednesday, people typically take the day off to be with the kids. It's a thing, it's a culture thing. So maybe the seasonal pattern is different for Wednesdays than it is for Fridays. So what you can also do is just generate such a season for every single day of the week. And you can even extend this trick to sort of generate a feature like this for every single holiday. For example, if you're buying Valentine's Day flowers, roses, then typically after Valentine's Day is done, no one wants to buy roses anymore, so the price for roses just drops. And usually it's all the days before Valentine's Day when the retail prices go skyrocket. So to accommodate these sorts of effects that are kind of like the season because they occur every single year, you can also make a feature like this that depends on when Valentine's Day happened. And you can still get away with a lot of doing things in just linear models, and you can interpret everything, and you can still tweak lots of stuff. Do that with your neural network. And that's part of the point. I mean, you can still generate all these features and chug them into a neural network. I mean, that's fine, but it's not the point. The cleverness of what I just did came from creativity by not focusing on the algorithm per se, but just started thinking about the problem. If you understand the solution better than your problem, you're doing it wrong. A thing to note, I mean, a lot of people would say maybe just chug it into some gradient-boosted machine or deep neural network, and I do hope that you shouldn't expect that auto-magically these features will be generated on your behalf. There's still something to be said, maybe nudge the algorithm a little bit and think along. I'll consider a small variant to show that even now we're still super flexible, because typically you don't have a season that just repeats itself every single time. What you typically have is something more like this, like there's some sort of change in the season. The season might also change over time. So, oh my god, can the linear model still accommodate this? Yes. There's a couple of tricks that you can do. So normally in a linear model, you do this thing where you minimize the error. So this is the squared error that you can minimize. There's other people that like to prefer to minimize something else, like the absolute error. That's also fine. There are some other people that say, oh, you can do this thing called ridge regression, where you basically punish it if the weights get way too big, which is actually a neat trick, and we can just write it down. What you can also do, and that's actually what I really like, is you can also say, well, you know what? Certain errors are more important to me than other errors. So stuff that happened 5 years ago, I care way less for than stuff that happened a month ago. So we do the same trick. Oh, by the way, if you do this, you can do this with like a gradient descent method. But if you're a math nerd, you can also just write it down in the matrix and there's a closed form solution. Super cool. But what you can also just do is you can make another column in your train data frame, call that importance. In scikit-learn, you can do this with linear models. I think support vector machines, logistic regression also have support for this, which is pretty cool. And what you have to do beforehand is you have to go to your pandas data frame and basically add some sort of importance. What I do here is I do some sort of exponential decay all the way to the back, and I have another hyperparameter for this. Stuff you can play with. This is what we had before. This is what we have now. And you can see we really don't care about the fit that happened in the past much more. But the thing that happens in the future is fitting better, even though it's still not perfect. But this is a simple trick we can just go ahead and use. So when you do this, I'm going over this very fast because I think I made way too many slides than I have time for. But one thing that when you're doing stuff like this, what you typically want to do is you're going to end up with a bunch of hyperparameters. And at least for me, whoops. Speaking of optimization, better check the cable. But at least for me, what I really like, there's these pipelines in scikit-learn, and they work very well. But part of the stuff that I'm doing here is in pandas. And you cannot really put all the pandas operations in these scikit-learn pipelines perfectly yet. So what I just do is I just make this one function that have all the hyperparameters as function inputs. And then I have some, it's a library called evil that I really like to play with. It does evolutionary algorithms, and it's good enough for my hyperparameter tuning in general. Do whatever you will, but keep it simple. That's the whole point. Another thing that we could do, just as another trick. This is a bit of syntax from R. In R, this would be a way for me to say, hey, I want to predict the variable y, and it depends on all the other variables. What I can also do in R is I can say, you know what? I want to have an interaction term. So don't just take the radial basis function that I had before, but just multiply it by the time. That way, the seasonal pattern might increase as time increases, because time increases, and it will multiply itself by that feature. This is the R trick. It's kind of like a DSL for model specification. But there's a cool library in Python called Patsy that allows you to take a string just like that, and it will generate these features on your behalf. And it works on pandas data frames. It automatically does one-hot encoding. It's a pretty sweet library. If I'm very frank, this is the first, when I saw that library, that's when I started doing less R machine learning and started moving to Python. It really helps. When you run this, this is what the xtrain looks like. So you still got the names of all the variables that you make. And you can see that we still get all the original variables that we're creating. The only thing that's been added is we also get the time times the radial basis feature, etc. It's pretty cool. It saves you a lot of typing. When you do this, though, you're going to generate a whole lot of features, and then you should probably want to reduce them as well. So things you might want to consider is maybe just get a ridge model to prevent overfitting. Try to maybe remove variables in your hyperparameter search function, because you don't want to keep things small. You can apply t-tests with stats models. You can also use whatever thing in scikit-learn for feature selection that you have. This is when we apply the sample weights. This is when we apply the sample weights and add the interaction terms. So some parts are predicted better. If you just pay a bit of attention, these are two predictions a year ahead that are somewhat reasonable, but I can think here it's predicting the end of the year a little bit worse, whereas here it was a little bit better. So it smells like hyperparameters. I think I describe a lot of text here basically that says, here's what I end up with, and it's pretty damn decent, which is the main point. And all of this was done with just simple models and a bunch of tricks, and I can still perfectly interpret the model. I can still play around with it. And here's a nice thing. Our example only had 3 years of data. So if we have that for every single day, that's only 1,100 data points. The radial basis functions works in such a way that different months can actually overlap in features. So I'm actually using as much information as I can to generate all of this. And, you know, try doing this with a deep neural network. I don't know if you need more than 1,000 data points. You probably do. There's something to be said, at least, that you shouldn't expect a recurrent neural network to automatically solve all of this for you. But if I have, let's say, 1,000 different products, I can generate all these different radial basis functions and just per product run this. And I should be able to filter out the season still relatively nicely. I can sort of, there's two types of machine learning models. You got the Panda, that's you really want to care for that model, you want to optimize it perfectly. But in this case, if I got 1,000 models I got to train, I think this is decent for a general seasonal fit. Linear models are easy to maintain and debug. If something goes wrong, we can inspect it. Linear models are actually kind of fast to train, which is also kind of nice. I train deep learning in production now. I have to wait sometimes. And they're also very easy to explain to humans of management, which, especially if you're a consultant, Lev, is a very useful thing. And here comes my favorite reason, and I didn't expect this at all, but when I'm running a deep learning model in production, linear models are convex. When the optimizer says I'm done, then I'm sure it's done, and it will not find a better place in the training set for a fit. When a neural network is done, it basically says, well, I don't have enough time to do anything more, but it can converge on something that's completely bonkers. And this is something I have to worry about in production. Besides all the other stuff I got to worry about, I now also have to check if the convergence is okay, because it's something I don't have a guarantee for anymore. TensorFlow is a cool tool, but it's even cooler if you don't need it. Okay, honestly, if you have a scikit-learn algorithm that's amazing, but you can also just run a SQL query, the SQL query is better, right? The same thing goes for TensorFlow. And again, don't get me wrong. I've put deep learning systems into productions, and I like the algorithms. They solve problems I couldn't solve otherwise. Especially in text nowadays, I'm seeing things that are amazing. But production is dangerous, and I don't want to wake up at 12 o'clock on a Sunday because something went wrong. I prefer to just have PagerDuty off as well. So, speaking of production. I've just done a lot of linear models that are just, normal static files, and we can do some cool things with it. But there's some extra tricks that you can do, and especially if we're considering production, there's this whole realm of machine learning that I haven't heard a single talk on PyData yet. So let's talk about streaming, because, if you think about it, instead of handling data in a batch, where we just have one giant file you want to learn from, maybe it might be preferable to think about it in a stream setting. In production, data will probably come in a stream. Usually, you don't have someone that says, here's a CSV file, please train. So typically, we get one data point at a time. And this is kind of what it looks like. If you do it in batch, what you typically do is you train some sort of function, you learn it, and then until the next batch is sort of done with training, an event comes in and you apply this one function, and that's sort of the prediction. Most machine learning algorithms trained are lambda functions of sorts. If you train with scikit-learn, something goes in, something comes out, same thing goes in, same thing goes out. But in the streaming situation, what you would have is, hey, every data point that comes in might actually update the model state. And there's something to be said about being able to react quickly to the world and not having to wait for the batch algorithm that's running on a daily basis. So there's an implementation in scikit-learn that actually sort of does this. But you can also imagine that things like Apache Flink or Spark Streaming might have some implementations that are interesting. So I'll give you a small explanation of how some of these algorithms work. This is a point that lives in space, and we're going to do a regression on it. And as far as this point is concerned, it doesn't care about the blue line or the yellow line. They both have an equal fit. They both go straight through the point. So these two lines are somewhat equal as far as that one point is concerned. That's what I just said. However, I can make a second plot. What I can do is, this is, again, the point and the line going through. And this is a plot of x and y. But next to it, you see a plot of the weight space. So this is the intercept, and this is the slope. And the blue dot here corresponds with this blue line, and the yellow dot corresponds with the yellow line. As far as this point is concerned, every single thing on this straight line is equal in terms of fit. But now suppose that I had some weights from the previous points that I've seen. Well, then I probably want to find the shortest distance from the original weights that I had up until that plane. Well, we have linear algebra for that. Just put it on there, orthogonal, you're done. And what we can then also do is, we want to move in that direction, but instead of overfitting, how about we take a maximum step size? It seems like a good idea, such that we don't make sort of very aggressive moves. There's sort of a bound there. And the idea then is, as a stream comes in, if my whatever classification or regression algorithm has a pretty good fit, then I maybe not update. So let's only update when we have giant errors. When there are giant errors, let's do a very aggressive update. This is called passive-aggressive algorithms, and I love the name. And turns out that scikit-learn actually has an algorithm, a linear regression, and I think also a logistic regression, for passive-aggressive algorithms. I've actually used this as a client, not so much for the benefit of the streaming aspect, but more in terms of the benefit that you also need a much smaller memory footprint. If you just have to handle data, one data point at a time, there's no longer a need to have the entire data set in memory. So if you're only interested in sort of preserving memory, already this is an interesting algorithm, let alone sort of the actual streaming phenomenon, which is also very powerful. So this is a very small experiment because there's still some stuff that can go wrong. There's this constant step size that can be big or small, and I'll just go over this very quickly. You can read the slides later. What you can do, here you see what the fit is, and here you can see what the weights are doing. And if I, in the beginning, say, let's, in the first 30 iterations, take a somewhat small step size and then also small after, you see that the fit is sort of all over the place. If I were to say, oh, let's just take very small step sizes at all times, you see it takes a very long time to even get near where it's supposed to be. But then you see that the errors are much smaller. Typically what you want to do is you want to be very aggressive in the beginning, that just the first 100 data points or so that you see, allow it to make huge steps, and then allow it to make only small steps. A thing that's also kind of cool about these algorithms, if this thing is deployed, and it's updating data point per data point, suppose now the world changes a little bit, this thing will react. This algorithm is actually able to change its weights over time. But management says we should implement TensorFlow. Anyway, this approach can be on a live system, and it's especially useful when you've got labels coming in that actually come in on the stream. It makes if you have real-time updating on weights, it's very sensible. And if the world changes, then you can do some cool stuff. Extra details on math are on the blog or in the original paper that I've referred here. And I immediately hear you thinking, dear heckler, like, Vincent, this is all great, but when do you actually have a situation where a stream of data comes in with a label? Because, you know, if you have the label, you don't need a prediction, right? Kind of true. But let's talk about recommender systems. So the nice thing about a recommender is when someone clicks on the internet, then I get a stream that comes in that says, yes, this user clicked that thing. So in this case, yes, I have a label, but I would really like it if I'm able to use that immediately to update some sort of system. When I'm in retail, it's very common for me that I don't see someone for over half a year, only for that person to come back with completely new preferences. Maybe half a year ago you wanted to buy a Jaguar, but now you've got a kid and you need diapers. I would really like to learn this in preferably 2 mouse clicks. I don't have time for the batch algorithm to update. And here's the nice thing. Typically you have a recommender system, and let's suppose that you do collaborative filtering. I think it's fairly safe to say that the features of an item don't change that often over time. But the features of this user might. And here's the cool thing. This rating that we're trying to predict, be it a click or an actual rating, that's a linear model if you're just doing collaborative filtering. And if you assume that these items are actually set, you can use passive-aggressive updating, and suddenly you can still do batch, right? You can still do the giant batch algorithm at night, but then during the day, we now have a nice little method to keep the model updated per mouse click. Still a huge engineering challenge, but I'm no longer thinking about, you know, accuracies and that kind of thing. I'm more thinking about how do I want to make a cool system. But management wants us to use TensorFlow. And this is a general thing I see go wrong quite often, especially when companies are sort of starting with this. Don't just think about machine learning in general, like think about machine learning, but maybe think more about system design, because you want to build a system that you leave at the client, not so much just an algorithm. Algorithm is thinking in just a notebook. A system is about actually making the world better. I just showed you collaborative filtering. We can do something that's way simpler and way better. Let's pretend that we're making a recommender for the Dutch BBC. And just the simplest idea that you could come up with. You can probably calculate the probability if you saw this thing I call I, some sort of Dutch show. What is the probability that you're going to see some other show? So what's the probability that you've seen I and J together? The problem with this algorithm, this can already be an algorithm, right? But the problem with this is everyone is probably going to be watching the news. So no matter what you watch, I'm always going to be recommending you the news if I use this algorithm. So just, you know, as a mental counterbalance, just some sort of accounting, how about I divide this by the probability that you're going to watch that content anyway? Okay, so the hope is that we're going to give you somewhat specific content, because I'm going to give you content that's often watched together, but I'm going to account for the fact that you may be pointing someone to popular content. And you can sort of make a hello world chart of what that might look like. So suppose that it is super, super normal that I and J are seen together, but the probability that you're going to see J is quite high, then this will be the rating score that comes out. But suppose that I and J together is less likely, but the probability of watching J in the first place is super low, then this is relevant to actually start recommending. And I hope it's very clear. This is a very intuitive probabilistic argument, but if this is in production, I can write this in SQL. In fact, if this was a streaming algorithm, this is just counting. And It's so simple. Okay, you can write in SQL, that's what I said. Then you can calculate very easily. Also, you can write tests for it. If one of these numbers is ever higher than 0 or lower than 1, something goes wrong. So you can actually write some decent unit tests for this. And all parts of the algorithm are actually very interpretable. You can even turn it into a personal recommender. Namely, take all the recommendations of all the items the user saw, multiply these scores, and boom, you now have a personal recommender as well. So, you know, it's kind of weird if people are considering maybe starting with deep learning for recommenders, and there's some very cool work being done in that space. I'll definitely not deny that. But if you're starting out with this, probably you need to think about these sorts of things more. And suppose that we're working at this theoretical company doing actual recommendations. There's an even simpler algorithm that we can do. We can also just recommend the next episode. And it'd be very awkward if this particular video service that is a potential client of mine never tried recommending the next episode first. If this is something they didn't consider, that's kind of weird. And if they never really implemented AA testing or A-random testing just to test their baselines, that would also be kind of suspicious. And if they were thinking about using deep learning instead, I don't know. Then they're probably not thinking beyond the notebook. And the hype around these algorithms actually can be super duper dangerous. So I'll show you 2 more examples to sort of show you, to sort of lure you back into the domain of simple models. And you guys are being a good crowd. I've already done 100 slides with you today already, so this is going well. One example is about video games, and the other example is about chickens. So let's pretend that we're a super enterprise business model. We have a video game service, and people are in a queue. The problem with this situation is that whenever people are in a queue and they want to play a video game, they probably want to play a video game against someone of the same skill. It super sucks if you're super good and you're playing against a total noob. It also super sucks if you're the total noob getting his ass whooped. So we need some way to estimate player skill. And let's in this case assume that we have a stream that comes in that can only say this person, this person won. And that's the only thing we can actually learn from. We don't know anything that happened inside of the match. I hope it's also very clear that if this service is going to help people, then we probably don't want to wait for a batch algorithm. After every single game, we want the state to update. And we want something simple. So just as a simple insight, the first way I would start thinking about this, if you've been playing this game for years, then I should be able to say your skill estimation is much more precise than someone who just came in and never played a single game before. So if we're going to represent skill, instead of having our representation be a single number, it might be a good idea to say, hey, skill is actually a belief. I have a belief of your skill. I don't know exactly what it is, but it's a belief. Okay, simple way to model this. Follow along. I've got a distribution for player 1. I've got a distribution for player 2. Then I've also got, because before the game has been played, they're independent of each other, then I will have a 2D distribution of these 2 players. Suppose that one of the 2 players won, I can just throw away all the probability mass on one side, just draw a diagonal. If player 1 was the winner, then probably all the probability density mass that was here has just been declared unlikely because the player lost. The only thing I got to do then is come up with a clever update rule that translates this back into sort of marginals for every single player. But one thing that's kind of nice to note is I typically also have like a margin around the diagonal, which also means that I can support draw games. If 2 players are equal, that also means that their likelihood should be equal. You can then make a small simulation to prove that this idea works. So these are 2 distributions of skill when 2 people get in. One of the 2 wins. You actually see that one gets nudged to the right, the other one gets nudged to the left, and vice versa. You can just simulate this to convince yourself that it works. And what you can also do is you can simulate what happens if one player is proven better than the other player. If these 2 will battle it out, the cool thing is, if the poor player won from the good one, there's going to be a huge shift in belief. If someone who was supposed to be poor winning from someone who's supposed to be super good, then obviously there'll be a much bigger change than when 2 people who are supposed to be bad and one wins from each other. It makes sense. It's sort of information theory basically at its best. Also, if the good player wins from the bad player, there's hardly anything that's updating. So I get a lot of common sense for free. Still, I would like to know if this works. So then you have to find a data set that proves that this works. So I went for Pokemon. What you can do is you can go to the Poke API, get all the data from all the Pokemon. You can go to fan websites. You get a formula that tells you how one Pokemon might beat another. And you can actually simulate Pokemon games. And after running this... I know. So this is usually the point in time when everyone gets tired. So this is like the small bit of energy that I give you so that you understand the final point of my talk. Anyway, before this gets meta. These are all the posteriors that you get if you run this. And basically, we have an original belief. We update it after we see a single game. That belief is then held on. That another game gets played. We update the belief again. And my conclusion is that Magikarp is the worst Pokemon. So I think it's safe to say that my algorithm works. Mewtwo is also in the top 5. So take it or leave it. Designing this algorithm was a whole lot simpler when I considered I don't have to find some sort of algorithm that fits my data set. No, ignore all algorithms. Just think about it myself. What makes sense to me? How would I model this with just common sense? And it's mainly the observation that I want to use distributions instead of just a single number for your scale that made designing this easy. But I really like the algorithmic freedom I'm giving myself. Got it, 5 minutes. This in particular really fits the Bayesian mindset well. And it's something that is worth mentioning. Because this is a streaming algorithm as well. And the way that you can sort of see this, the distribution of the belief, this is all math, if you think this is boring, sleep for like 10 seconds, but the belief that I have after seeing 3 data points is my prior, that's sort of if a new person comes in, times some sort of update for seeing the first data point, the second one, the third one. Hey, look, the system is recursive, we can do streaming. This is a very general thing. We have a nice little system that we can define. And in layman's terms, if you come up with a sensible update rule for whatever we know before, we see a data point. If you just come up with a update rule that updates a probability, you're done. And it's lovely. And if you do the math, you can also do this for teams. There's a separate talk I did at Berlin Buzzwords. Look at that if you want to know how to do this for Heroes of the Storms. The thing in this is, and I hope it's clear, the model I've created is just a histogram. But look at all the benefits we now have. We can quantify the uncertainty, we can apply the model in a streaming setting, and it's very easy to deploy, understand, debug, and test, because we understand every single step here. And if you want to come up with such a model, my best advice would be take a step back from the hype, and sort of just, have a beer, pen and paper, sit on a terrace a bit, and just think about how you would prefer to solve the problem if you were not constrained by the machine learning tools that we have. We're blessed by them, I know this, but you're also cursed in a way. Let's talk about chickens as a conclusion, and I think I won't be running too much out of time. This is my favorite data set. Whenever I give trainings, I always say something about the chick weight data set. The idea is there's a diet, and there's a certain chicken that belongs to that diet, and at this point in time, this chicken was on this diet, and it weighed this much. And we can make a plot of it. And this is also one of those data sets that makes me a proud vegetarian. The idea here is there's a farmer who tries to get the chickens as fat as possible in 21 weeks. And this is sort of an A/B test on different diets. So what some people might do, if you were to do this in R, they would say, you know what, I'll just hot encode the diet parameter, and I'll put in the time. I'll just make some sort of linear model, and then there's a dummy variable for all the diets. This model is wrong, and I hope you all agree. Because if I'm at point 0 here, all the weights are almost the same. If at time 0, all the diets are about the same. But the model that I just proposed suggests that there's some sort of constant I have to add depending on the diet that you're in. That makes no sense. All wrong, all wrong. Now, because I also like to do things in R. In R, there's a very cool trick. You can have a data frame inside of a data frame. So what you can do is you say group by diet, nest it, then you have a data frame within a data frame, and then you can run a machine learning model per data frame. So the idea is per diet, I'm now going to run a separate linear regression, which is already much, much better. But it's still wrong. At least we're going to get separate slopes, but it's now possible that the intercept's not the same. And, I've got a bit of prior knowledge. A chick has been born. They all should have about the same weight. They're coming from the same distribution. Any model that does this differently is wrong. So the conclusion then kind of is, I just want to grab a piece of paper, write down this formula, and say, this is how I believe the world works. The weight is modeled by having some sort of constant for all the chickens, and some sort of slope, not an intercept, some sort of slope that's different for every chicken that's based on the time. And the only thing I want is the computer to look at this and maybe have some sort of domain-specific model, and I just want it to run. In R, there's a cool DSL called rethinking, and there's a function there called map2stan. And it's kind of like PyMC3. It's also kind of what Edward tries to do. And the cool thing here is I can actually sort of have a domain-specific model where kind of the features get generated, but also kind of the model gets defined. What I'm doing here is I'm saying, look, there's some sort of distribution that defines the weight. It's dependent on mu, which is some sort of intercept times some sort of slope times diet. The slope is different per diet. And this engine is clever enough to notice, hey, everything that's defined that's not in this data frame, that's something I have to estimate. And you run this, it compiles down to SAN, and I'm running over time. Just hang on for a moment. There's a break afterwards, right? I'm almost there, trust me. And this will get trained. And because this is a full Bayesian framework, you get some nice benefits. Namely, what you get is you get some uncertainty around the parameters that you estimate, which is also kind of cool. But I can go a step further. Because if I look at this data set, I'll see the variance increases over time. So I probably want to model that as well. OK, make a new thing on the back of my envelope. And then I add a couple of extra parameters to this one function. And lo and behold, it trains all of this. And the nice thing is, in this particular case, I can actually inspect the model. I can confirm that this works way better. But I'm actually dealing with uncertainty here as well. So I can actually sort of say, hey, the diet for the beta parameter for diet 3, that's super high. Oh, and diet 3 has a much lower variance than the other one. So diet 3 is probably the best. A neural network usually doesn't allow me to do inspection of models as detailed as what I've just shown you. And there's something very precious happening here. Instead of modeling in the feature space, we can also keep models simple by modeling in the model space. All sort of features that are automatically generated by this DSL make creative modeling somewhat convenient, and that's the thing I really like. And you can do this for house prices. You can do this for diseases that have certain symptoms, but I'm running out of time. So let's do conclusion time instead. I hope that I've somehow inspired you, or at least convinced you that these simple models are still a worthwhile pursuit. Feature engineering can definitely still save the day. And it makes sense to come up with systems instead of just simple algorithms, instead of mere algorithms. Simple algorithms are cool. Simple algorithms have properties that complex algorithms are simply missing out on, and we should care about more than just error in the test set if we want to provide a service. I hope I've given a glimpse of all the other things that you could be looking at that are actually highly beneficial. And especially in the case of the recommender, would you rather have a recommender that's 1% better, or a recommender that's maybe 1% worse, but can update for every single mouse click that a user sees? You may be optimizing the wrong thing here. Simple models can actually be very advanced and smart. Complex models can actually be inarticulate and dumb. Unfortunately, there's a fear of missing out. It's a dangerous pursuit. But let's start celebrating the fact that we can still get simple models to production. Simple models are easier to explain, understand, debug, maintain. So let's use them to solve problems. Time, right? Okay, so I definitely ran out of time, but this is 145 slides, so we did well. Yeah. Great. So here's the awkward thing. I'm between you guys and beer. So if you want to have questions, we could do them now. But if, oh wait, no, we're not. But there's a key, wait, no, Holden's gave an amazing talk after this. I'm not between beer. But we should, and also we have to make this space because Holden's going to give an amazing keynote in a bit. Because the walls have to be removed and stuff, right? Or do we have time for questions? Oh, we have 5 minutes. Time for questions. Yes?
Vincent.
Yeah.
Thanks for a great talk.
Oh, yeah.
Over here. The response I usually get, when I make this pitch is like about scalability.
What pitch?
The idea that linear models should be used over, deep learning. And they say, oh, okay, well, the feature engineering is really great, and you showed me a really cool example. But what if I have like a huge number of features, and I don't have time to do all of this feature engineering? I don't have the resources.
Well, so feature engineering can be partly automated, right? Mm-hmm. And feature engineering is not a convex solved problem, so you're not going to do it perfectly anyway. And if you just try a couple of simple ways to do feature engineering automatically, you can still manage a lot of things, I think. And again, the examples that I showed you were sort of obvious things where there's domain knowledge available to actually get the thing done the way you want it. But there are, of course, still situations where it might make sense to go a different route. That's fine. But consider the simple thing first. Don't do the complicated thing before you've benchmarked the very simple thing, which includes recommending the next episode, for example.
Thanks.
The argument against linear models is not so much XOR, but the typical argument is outliers, especially when linear models are used with somewhat naive error metrics.
Sure. That's not a question, but I'll respond anyway.
No, I mean...
or is a response not required?
So basically, when you're working with linear models, what's your favorite way of dealing with noisy, messy, outlying data?
Sure. My favorite way, and this is only if I've got time for it, and again, there's this notion of there's a panda, there's a model that I have to take very careful for, because with this one model is super important to everything, and there's also these situations where I just run 1,000 models that are all time series, and I have to care less per model. But one thing I like to do, but it's also because when it helps me to understand the data, this is an example where I have also defined how noise works. So I'm actually saying here, look, the noise is going to increase over time. And also how that noise is increasing, for that I've got uncertainty bounds that are coming out of my model. So preferably, I prefer to do domain-specific modeling. And this is cheap, by the way. Usually you go to a retail client, you just have a coffee with, I don't know, a truck driver or someone who's actually doing the work on the floor. And typically they will just tell you how to do this. Not necessarily by saying, oh, the outliers in sigma. No, they just actually tell you how this works. But But then on your side, you can deal with the uncertainty however you want. You just have to model it appropriately. And that's still the art. It's not a solved problem, but you can manage, kind of.
Another question.
Oh, yeah.
So up to now, you've been showing us how to basically do feature engineering as a support vector machine would be doing it. Are there any other ways that you would recommend?
Okay. Just to translate, I'm not saying that all complex models are evil and should be put in the dungeon, right? The main argument for starting with simple models is, if nothing else, see it as a benchmark. And the simplest example for classification would be take the most frequent class. And especially when you're doing things with recommendations, the thing that annoys me so much is the thing that people never do. When you do your first A/B test, do an AA test. That way you can test if your A/B splitting works, because you don't want to be making decisions for 5 years and then realize, oh, none of them mattered. And the next thing you should always do is do an A random test. Why random? Because it's the worst possible recommendation ever. Just do random stuff from all of your content. But you will at least measure how many people will click anyway. Knowing this, and then realizing, oh, my recommender is only 0.1% better than that, means you haven't figured out how recommenders should work on your platform. If nothing else, start simple this way. And the main reason for it is because otherwise you don't know what's happening. I think there's one more.
I guess not like specific to the linear model versus deep model thing, but more about streaming. So
yep.
How do you account for the fact that as data comes in, you might be overfitting for each data point, or like history bias, or like reliability?
Super good one. So, whenever something goes to production, someone has to just give me a reason why it's a good idea. And some people might also say, hey, doing it this way is not a good idea. But just as a general architecture for this specific case, I could argue we can still do the batch thing, run that every night, and just what happens during the day, we're going to do in a streaming fashion. And then I can already limit some of the things that go wrong, because probably the world's not changing overnight every single day. Another thing that you can do if you're worried that you're maybe overfitting a bit, in the example that I gave on passive-aggressive, there is this maximum step size that you can specify. So there are some sort of tricks that you can deal with this. In this particular case, though, the main thing that I would do is start monitoring this. Because everyone can sort of do hand-wavy arguments that, hey, this could happen, that could happen. Sure, everything can go wrong. But maybe start measuring it first and then still getting it live first, making sure the whole pipeline works. That's a good investment either way. So your concern is definitely valid, but measure it first, then optimize. But very valid concern. Holds for deep learning, too.
Any more questions?
Okay. In that case, there's still tickets for PyData Amsterdam. We're looking forward to serving everyone stroopwafels. Thanks for listening. Oh, wait. And if you can all do me a thing, we all hate recruiters on LinkedIn, right? So what you can do to sort of annoy them a bit, this is my actual LinkedIn profile. What you can sort of do just for fun is you can list all the big data technologies that you're using and just chug in a few Pokemon names and just ask the recruiters if they can understand which of these things are Pokemon and which aren't. If we just all promise to do this right now, LinkedIn will be a much better place. Thank you.